Okay, so in this video, we're going to talk about isotopes and atomic weight or average atomic mass. So the learning objective here is that we're going to understand what isotopes are by definition and by application, and then we're going to also talk about atomic weight and how we could figure that out through the use of calculating relative abundances and the masses of isotopes. All right, so first, all atoms of a given element have the same number of protons, but they may not have the same number of neutrons. Thus, they may differ in mass numbers. And so, for example, right, we have a carbon 12 and a carbon 14. Okay. Now, because they're both carbons, they have the same atomic number. All right. And so, if you look at the periodic table, you can find the atomic number there. Sometimes it's written on the chemical symbol, but which this time around I did not include it because oftentimes this is the way chemical symbol is often shown. All right, using just the element and the mass number, and if applicable, the charge. So here we have a carbon 12 and a carbon 14, and if you look at the periodic table, that we see that both these carbons have 6 protons. Okay. That we know, that we see. But then what makes the biggest difference between this carbon 12 versus carbon 14, the mass numbers, is the number of neutrons. Okay, so the first carbon that you see there, a carbon 12, has 6 neutrons. Okay, carbon 14 has 8 neutrons. And so here we have what we call isotopes. Okay, these two carbons are isotopes of each other. All right. They're the same type of atom. All right. Because they have the same number of protons, but because their number of neutrons differ, this is what makes them isotopes of one another. Okay. Let's look at another example. Hydrogen has 3 different naturally occurring isotopes. We have protium, deuterium, and tritium. Okay, protium has 1 as a mass number, deuterium has 2 as a mass number, and tritium has 3 as the mass number. Now, if you notice, all of them have the same atomic number, okay, or all of them have the same number of protons. Okay, and so for each of them, I show that the protons are notated by that red dot. Each of these atoms all have 1 dot, so 1 red dot, so that shows you that they all have 1 proton. All right, but if you also look more deeply, is that your number of neutrons changes between each of these atoms. So protium, or hydrogen 1, has no neutron. Deuterium, or hydrogen 2, only has 1 neutron. Tritium, or hydrogen 3, has 2 neutrons. Okay, and so that's kind of the biggest difference between these 3 hydrogens. Do they have the same chemical properties? Yes. All right. Do they have the same physical properties? Yes. The biggest difference is just structure. All right. That they don't have the same number of neutrons, thus their mass numbers are different. All right. Now, but most naturally occurring elements, much like you see here in hydrogen, they're just mixtures of isotopes. Okay, and so if we were to take a large sample of pure hydrogen, all right, what you will notice, all right, that about 99.985% of all the hydrogens in your sample is protium, or hydrogen 1. All right. And the other 0.015% will be deuterium, or hydrogen 2. All right. You're probably asking what happened to tritium. Well, tritium is extremely rare isotope of hydrogen, which it's been only measured in like trace amount in nature, and more specifically in the upper atmosphere of Earth, where the UV rays hit the atmosphere. And this is kind of the time where tritium tritium is produced, all right? But it's very, very low trace amounts, to the point that we don't even calculate it, all right? So it is useful to know the average mass of atoms in a larger scale, all right? And so this average is called the atomic weight, or we often call it the average atomic mass. And so for hydrogen here, the average atomic mass is 1.008 AMU. All right. And so this is another number that you could find on the periodic table. We mentioned in the last video that you could find the atomic number on the periodic table. There's two sets of numbers that you could find on the periodic table. One is the atomic number, and the second is what we call the atomic weight, or the average atomic mass. Now, the average atomic mass is often a decimal number, simply because you are, or in many cases, that average atomic weight tells us what is the average of the mass of all the naturally occurring isotopes of a particular element. So this is the reason why it's typically a decimal number, because it's just an average. All right. And so if you consider the element hydrogen and all its three naturally occurring isotopes, we see that the average weight of all the atoms is 1.008 AMU. Okay, so now let's talk about how we calculate this number. How do we come up with this number? Okay, and what does it mean? Like when we look at the atomic weight, what information can it tell us? All right, and so this is where we kind of delve out just a little bit deeply. All right, and so let's just kind of stick to hydrogen here, because now we have the numbers. So atomic weight, or average atomic mass, is what we call a weighted average. All right. Now, if you remember from the days of high school, right? And when they're calculating your grades, most of the time in most high schools, your grades is based off of a weighted average. It's not just a straight average, but a weighted one, okay? And what do I mean by a weighted one? Depending on the type of assignments, depends on how weighted it is in your overall average. Okay, so like, for example, you may have different categories, such as, I'm gonna put this here, test, classwork, homework, project, quiz. All right, and so and depending on your teacher, they may have different weights for this. So for example, maybe 40% of the class, 40% of your average was your test, 10% was your classwork, another 10% was your homework. Then let's see, you'll have 30% of your grade was your project, and then you may have last for your quiz is probably another 10% of your grade. All right. And so now, depending on what type of assignments you have, and your grades greatly affects your overall average. And so if you look at, this grade breakdown, obviously, the assignments that were labeled tests weighed more than any assignments that were labeled classwork. All right. And so when we think about your overall average for the class, all right, the overall average basically was affected by two different main aspects. And those aspects are, one, your grade, the grade of that particular assignment. Like, what is, did you make a 95? Did you make a 23%? Whatever the case is. So the grade, and then it's also affected by the percentage of whatever category that it is in. So that's your overall average, and that's how it's graded, right? So you have the actual grade of the assignment and the percentage that's attached to that category. So when we're talking about average atomic masses or atomic weight, it's the same idea, because it's a weighted average. And so it's affected by two main aspects. One, it's the mass of the isotope. All right, so I'm going to kind of write this down. So your atomic weight, all right, and how it's calculated, all right, it's going to be the sum, because the symbol means sum, all right? It's the sum of, you have the mass of the isotope, all right, multiplied, all right, and obviously there's a percentage that kind of goes with it. And so multiplied by what we call the percent abundance of the isotope. All right, how frequent is it? You know, of all of this type of element, how many of these atoms have a particular mass number of X, and what's the percentage of the other isotope that has the mass number of Y? Okay, and so when we're looking at this case here of hydrogen, okay, what we have here, we have the mass, all right, which is going to be simplified in this case as just the 1, but most times you'll know exactly by the decimal point what is the mass what's the mass of a particular isotope. All right, so we have the mass number 1 here, and then we know also what is the percentage of this isotope that exists in nature. And then you have the second isotope here with the mass of 2, and then we know what's its percent abundance that we find in nature. And so you could kind of just plug this into the to this equation here to figure out what's atomic weight. And so the atomic weight in this case, all right, if we're calculating for atomic weight of this of hydrogen, all right, so we have the mass of the isotope. So let's look at the mass of the first one. So the mass here is 1 times its percent abundance, which is 99.985%. Make sure you use a percent sign when you're calculating this, okay? Plus, that's the sum part, right? Plus the mass of the second isotope, which in this case is 2, multiplied by its percent abundance, which in this case is 0.015%. All right, so we're going to include the percent here. And so make sure you also include that if you're using the calculator, you press the percent button. If your calculator doesn't have a percent button, then all you have to do is just take that number and move the decimal 2 times to the left, okay? And so when you plug this into the calculator, you'll get 1.008 AMU. That's the average atomic mass or the atomic weight for the element hydrogen, okay? Let's look at another example. There are 2 naturally occurring isotopes of chlorine, okay? So we have chlorine 35 and we have chlorine 37. All right, so the mass of chlorine 35 is 34.97 AMU, okay? While the mass of chlorine 37 is 36.97 AMU. Now, in nature, chlorine 35, of all the chlorines, all right, chlorine 35 represents 75.77% of all the chlorines, okay? While chlorine 37, the other isotope, represents 24.23% of all chlorines that exist in nature. Now, the question here is, then what is the atomic weight of chlorine? Now, the good news here with this type of calculation, you could easily check your answers, right? If you go on the periodic table, you'll see the number there. So if you got to work through the calculation, then all you have to do is look at the periodic table and you say, oh, okay, it's the same number. Great, I did it right. Now, if you didn't, well, then we're going to have to kind of backtrack and see what happened, what we went wrong, okay? But anyways, let's jump into this problem. So as I said earlier, the atomic weight, okay, is equal to the sum of the mass of your isotope multiplied by its percent abundance, all right? And you want to do that with all the isotopes. All right, so let's kind of look at this situation here with chlorine, okay? And so with chlorine, the atomic weight, we have the first isotope, which has the mass of 34.97. All right, so 34.97 AMU, all right, multiplied by its percent abundance here. So 75.77%. Okay. And we're going to add it because there's another isotope. So if you're dealing with a atom that has 4 isotopes, you're going to do this 4 times. All right. Or you're going to have 4 sets of numbers that you're going to multiply and add together at the very end. All right. If you have 10 isotopes, you do the same thing. All right. But in this case, we only have 2. So we have 2 sets of numbers that we have to multiply, and then we'll add them together at the very end. All right. And so here's the mass of our second isotope. So the mass is 36.97 AMU. Multiply by its percent abundance, which is here. So it's 24.23%. All right. So when you add these numbers together, when you multiply the mass and the isotopes, the mass of the isotopes and its percent abundance for each of them, and you add them together, you should get 35.45 AMU. Okay. And so that's the average atomic mass for chlorine. And as I said, you can go on the periodic table, but just make sure your answer is really, really, really close to what we have here. Okay. So this is how you calculate average atomic mass.